Hi guys. All right, so we're going to start talking about titration. So learning objective 5.6, we have one more learning objective in unit 5, and then we'll move on to unit 6. All right, let's talk about what a titration is. So real quick, titration is essentially a technique that we use in lab. Sadly, you're not going to be able to do titrations in lab. It was actually probably one of my more fun experiments I got to do as a chem major. And so you use it to determine the concentration of solutions, okay? Acid-base titrations are what we're going to be dealing with. You can have other types of titrations, but the big idea here is you use it to figure out the concentration of solutions, okay? Acid-base titrations are based off the equations that we've talked about so far. Acid plus a base gives you salt and water. To figure out the concentration, to figure out the moles, to figure out what we have, because we're usually going to be using a 1-to-1 ratio, we can use the M1V1 equals M2V2 or dilution equation. Note though, in a titration, one of the cool things about it, so I will post a demo video on what a titration looks like. The volume is continually changing because you're adding stuff or liquid as you go along. Okay, so because the volume is changing, your ICF table has to be in moles or millimoles. So there are three terms that we use in titration that you do need to know. The titrant is whatever is in your burette, so it's what you're actually adding. The substance titrated is what is in your Erlenmeyer flask. All right, so you have a set amount of that, and then you start adding a certain volume of your titrant. And the equivalence point, this is actually very important. The equivalence point is where the moles of the substance titrated equals the moles of the titrant added. So you hit a point where it's a 1-to-1 ratio, you have the exact same number of moles for both. All right, so three kinds of scenarios or situations where we can use titrations. If you're doing a strong acid, a strong base, you're always going to get a neutral salt, and you can use titration to figure out the concentrations. Weak acid, strong base, you get a basic salt, and yes, you can use titration to figure out concentrations. Same is true for a strong acid, weak base. However, for a weak base, weak acid, you cannot use titration because it's an equilibrium reaction. You're not going to completion. Okay, please note, you cannot skip ICF tables in dealing with titrations. You have to use your ICF tables, and you have to use it in millimoles or moles. But again, if you're doing it in moles, you have to remember to convert back to molarity because it's concentration that we're usually going to be dealing with. So when we talk about titration, I'm not going to spend too much time on this. I will post a video that shows how titration happens, but essentially if you're in lab, you would get what you needed, make sure that you have your volume of the substance titrated in your Erlenmeyer flask, put your stuff in the burette that you're going to do your titrant, and essentially just add. You have to add an indicator as well that shows the color when you reach that point, the equivalence point. Essentially just add your titrant till you hit that point. I will post a video later showing how to do that. So when you're dealing with titrations, there are two main calculations that you're going to do. Figure out what the equivalence point volume is, or figure out what's going on at the equivalence point, and then you can also determine what's going on through the entire titration. You can figure out the pH at the start, the pH at the equivalence point, the pH at all points, and the pH past equivalence point. So those most of the math that you're going to be doing dealing with titrations. Here's a sample titration plot, okay? Right here is our equivalence point. That's the point where the number of moles of the titrant equal the number of moles of the substance titrated. It's a very important point. It will change based off if you're dealing with a strong acid, strong base, or a strong acid, weak base, or strong base, weak acid. But essentially, this is what that would look like. We're titrating the volume of whatever the titrant is that we're adding versus the pH. Okay, all right, so that's what a titration curve looks like. Remember that at the equivalence point, this is actually what is most important. the moles of the titrant equals the moles of the substance titrated. That's why it's the equivalence point. No, it doesn't have to be at a pH of 7, but all we're saying is, hey, at that point, we have the same number of moles for both. One drop before the equivalence point would be acidic. One drop after the equivalence point will become basic. So if we go back here, one drop before this, my substance is still this way, it's acidic. One drop after this, my substance goes that way. In terms of pH, it becomes basic. All right, so there are 3 different pHs that you can have at the equivalence point. It's either going to equal 0 if you're dealing with a neutral salt, so strong acid, strong base titration. The equivalence point is always going to be 7. Did I say 0? I apologize. The equivalence point of a neutral, the pH at equivalence point of a neutral salt, always 7. If you're dealing with an acidic salt, the pH is going to be less than 7. If you're dealing with a basic salt, the pH is going to be greater than 7. So those important for you to note. Okay? So sample calculations that you can have regarding this. So if you react a strong acid or a base completely, you need to keep track of how much stuff you have using your ICF tables, okay? We've talked about that in dealing with buffers. The only difference now is we're not at equilibrium, we're going to completion. Once you react all your strong acid or base completely, you need to figure out what you have left. Again, using your ICF tables, you can figure out what you have left. If you have a strong acid or a strong base left, because we know strong acids and bases dissociate completely, you can figure out the pH or pOH by literally taking whatever moles you have, convert into concentration, and that's what you can use in the pH-pOH equation. If you have both a weak acid and a weak base left in solution, you have to use the Henderson-Hasselbalch equation. Okay, if you have a buffer solution, your weak acid conjugate base, you have to use the Henderson-Hasselbalch equation. And then finally, if you have a weak acid or a weak base, one or the other, you would use the shortcut, and we'll talk about that in a little bit, to figure out the pH or the pOH. Here are the equations. The first equation you would use if you had a strong base or a strong acid left. Okay, so you do your analysis, you have your final solution. If you're left with a strong acid or a strong base, you can literally use your hydrogen ion concentration, OH ion concentration to figure out the pH. You would use this if you had a buffer solution left. Okay, Henderson-Hasselbalch equation. And you would use these two. So for this one, if you only had a weak acid left, and this if you only had a weak base left. Again, we've talked about all these equations, but the big idea here is being able to know which one to use. So you have to analyze your solution, figure out what you have in that final solution, and then figure out which of these equations you'll be using to find pH. So for example, I'm adding 10 milliliters of 1 molar NaOH to 75 milliliters of 1 molar HNO2 solution. The first thing I'm going to do is figure out how many moles I have of both. Okay, so I figure out the moles of NaOH by multiplying my volume by my molarity. Remember, big M, where do I write that? Big M equals moles over volume in liters. Now, for those of you that want to keep this in moles, that's totally fine. That's 0.01 moles or 0.075 moles. Either way works. Okay, so first figure out how many moles you have initially. Next, plug into your ICE tables to figure out how much you're going to be left with. So I have these many moles of my base, these many moles of my acid. I'm going to react all of my base. So I react everything that I can react, which is why it's minus 10 here, but plus 10 here. One of the key things in writing your ICF table is being able to write out this equation correctly. And so my final would be this, final that. In this case, so the third step is figure out what you have. I'm left with HNO2 and NO2 minus. What kind of solution is this? What kind of reaction happened? What am I left with? This is a buffer solution. And so what equation are you going to be using? the Henderson-Hasselbalch equation. Log of the base over the concentration of the acid. And then you can figure out your molarity. Make sure that you convert these back to big M, molarity, and then you can plug in to find your pH. Okay, so that's essentially what we're going to be talking about for the next couple of video lectures.